Hello, so welcome back to Periodicity. This time we're on part 3. So for this one what we're going to look at is the trend in atomic radius of the atoms as we go across period 3, or atomic radii. So quickly, it's just to catch up where we're going. So periodicity 1, we covered the general structure and arrangement of the periodic table and look at some groups and that we need to know about. Then we looked at how the melting point and boiling points changed as we went across period 3. And today we're going to be looking at the atomic radius, as I mentioned before, and explaining that. So again, a bit of recap. Where were we last time? Well, we looked at how the melting points and the boiling points changed, and we explained this in terms of the structure and bonding. So our first 3 elements going across the period, the sodium, magnesium, aluminium, we saw a general increase in melting points and boiling points as we went between those 3, and we explained that in terms of their metallic bonding. So sodium has 1 valence electron, so that would be delocalized, leaving a 1 positive charge on the metal ions in the center. Magnesium would have 2 and aluminium 3, so we had a greater electrostatic attraction between the metal ions and the delocalized electrons, meaning greater forces. Okay, so then we looked at silicon here. This was almost an anomaly in terms of the structure and bonding, because this one was macromolecular, or giant covalent, and consequently there are many covalent bonds that need to be broken to turn it into a liquid, and then subsequently into a gas. And then we got our simple molecules here. So these, we just had weak intermolecular forces between the molecules. So we got a relatively low melting point, boiling point. And then argon had the lowest because that is atomic. Okay, recap took rather longer than I expected to do. Okay, so here we go. Trends across the period. So we've got atomic radius here. No, let's just reactivate my pen. Okay, so here we go. There's the atomic radius here, and we can see in our graph down here how as we go across the period, then the atomic radii decreases as we go across. Now you notice I put ignored over here for argon, and that's mainly due to the way that we sometimes measure atomic radius. Now you may see some data where they've put numbers in for this. Generally speaking, in terms of our A level, we ignore this. It's just mainly because there's different ways of measuring atomic radius. It isn't as simple as you might imagine. So I've got down here, we've got measuring covalent radius. So what we look at here is we imagine, say we've got chlorine, because we know it fast forms bonds. So I've got 2 chlorine atoms, and they will overlap because they share electrons and form a molecule. And what they do is they look at the distance between the 2 nuclei and then halve it, and that is what they consider as being the atomic radius. Okay, so it's half the internuclear distance between the 2 atoms. Okay, you don't need to know much about that, to be honest. I'm just including that just for reference. Okay, so now we've got to explain the trends as we go across the period. And this all boils down to nuclear charge. So as we go across the period, the nuclear charge increases, so it's the number of protons that we have in the nucleus. And that is the direct link. So the explanation for that is, turn onto this page. Okay, so this is how we increase the nuclear charge, but at the same time we are not significantly affecting the shielding. So okay, we add an extra proton and we add an extra electron as well, but that extra electron doesn't really interfere with the interaction between the nucleus and the outer electrons. And if there's no change in that, then it's this nuclear charge that has the biggest effect, and that's going to pull in those outer electrons. They're going to be more tightly held and they're going to draw in. So it's a lot like the ionization energy topic that you might have looked at before. And I like to use the analogy of going to a concert. So if you're at a concert, you've got a band on stage. There's my little man. He's got a microphone and he's singing. Okay? So if someone goes into the show and they line up and they're watching it, so we're going to fill from the front first. Okay, so this is like representative of our first energy level. Okay, this row of people. So we're filling the third row. In fact, here aren't we, because it's period 3. So then you might have another row here, blah, blah, blah. A load more people. They can't see the stage quite as well as the people at the front. And more people that go to the audience, they're going to be able to afford more artists to go on stage. So here we've got some backing singers over here. And here we've got some dude with a guitar. Okay, so now, so that was the second, and now we're on our third row of people. So the first person comes in, here he is, and he can't quite see the stage quite as well because there's all these other people in the way. But then, when the next person comes, so he paid his ticket, so they go, oh, we can put some more money on stage, so we're going to put an extra artist on the stage to make it a little bit more attractive. So now when our next guy comes along, he fills in this row. The fact that this person appeared first doesn't interfere with his line of view of the stage, because we fill in the same shell. So his experience at the front is only going to be the same as the other person. So over here we're getting more things going on. Okay, there's a greater nuclear charge, is what our analogy is. But there's no change in the shielding. Okay, so hopefully you got my silly analogy, but there we go. So what have we done today? So we've looked at describing the trend of atomic radius decreasing across period 3, and we've explained this in terms of the nuclear charge of the elements there. So there's more protons as we go across the period, and they're going to bring with them extra electrons, but those electrons do not affect significantly the shielding. So there is a greater